What are you expecting out of bosons and fermions? Welcome back, everyone. We're jumping right into the heart of Chapter 5, Section 1, focusing on two-particle systems. This time, we're aiming to determine the expectation values of the separation distance between various interaction types. Here, the problem states that we wish to imagine two non-interacting particles, each of mass m, in the infinite square well. If one is in state �ψn, equation 2.28, which is not actually the solution equation, so I'll just go ahead and modify that in the PDF, and the other is in state 𝐶l, where L is not equal to n. Remember, fermions cannot stay in the same state. They don't get along. Calculate x1 minus x2, where that is the separation distance in one dimension, squared, assuming that A, they are distinguishable particles, B, they are identical bosons, and C, they are identical fermions. So this will be interesting to see, and we'll see how various that expectation value breaks apart. Before we begin, however, there is a free companion PDF for you to follow along, because some of the stuff just gets tedious, might be fast-paced, slow-paced, and you just want to see it. Totally fine. Access it using the link below, and you'll be good to go. Alright, so without that, let's dive into this question and see what we need to do. So, heading into stop number 1 then, I think it's important that we reference an old friend of ours, namely the infinite square well. And we see here that we have two states color coordinated in green and blue, and we see that the solution to that infinite square well, the wave function, was given as such. It should be burned into our memory by now for how much we use it, but let's also save ourselves some time in calculating these things for this question, because we actually found the expectation value of x and x squared for these states back in problem 2.4. And yes, I will link that below because it has been quite some time since we've seen it. That being said, when we want to jump right into this and see what we are dealing with in case A for distinguishable particles. Now, if you're following along at home and you are in the book, we see that we have this nifty equation here. And this equation was derived in, I think, section 5.12, something like that. Its equation number is given as 5.23, and that is in the new edition, the third edition of this book. So be aware that that is available for you, and the PDF has the links accordingly. But let's take a note here that this kind of looks like something we might expect out of a separation distance expectation value. Namely that we have a square here for one state, a square here for another state, and these cross terms. We've kind of seen that before, so it's not too unexpected, but be aware that these things do get a little more complicated in the case of identical particles. So with that, all we need to do is plug in the values that we found from the previous exercise, which Griffiths is great at doing. He makes you do a bunch of exercises only to use those results later, and that saves us a lot of time so we can get back into the heart of the theory. That being said, we need the x squared of the end state, which is given in green here, same as the blue here. So we see the only thing that changes is the n and the denominator here and here. And then we see that with the expectation value for n and L of just x itself, that's just a over 2. Remember that we're kind of expecting it to be in the middle of the well if it's an infinite square well. So that kind of makes sense geometrically. That being said, now that we have this down, it is very algebraically messy just to simplify this. So let's see how we do that. Alright, so once we cancel out and simplify everything, kind of split up that denominator, we see we just get pi squared, n squared, and all that other fancy jazz just from distributing and all the stuff we need to. Let's note here that every term has an a squared in it now, so let's factor that out. Then we have a 1/3, 1/3, and a 1/2 that we can combine. That gives us 2/6, 4/6, and 3/6. 4/6 minus 3/6 gives us 1/6, so we're good there. We notice that we could split up these fractions here and just keep the state in the denominator by itself, which we do. And you see both of those states have a 2 pi squared, so we're able to simplify this relatively quickly and get through part A. Factor out the a squared from every term. We see we have a 1/6 from all the fractions, a 1 over 2 pi squared from the states themselves, and this nifty little parentheses here. That being said, this is the conclusion of part A. we got through the distinguishable particles without any worry. That's pretty nice. Now, what's fancy about this is we actually get to use this result in the next two parts, but we have an extra term for the overlap of these identical particles. Let's see what that means. So, we saw what the expectation value was for the distinguishable particles, which was equation 5.23. Now, in part B and C, we have identical particles. And if we're bosons, that infers the upper sign of equation 5.25. So let me write that here. We have equation 5.25. And as you see, we get the distinguishable expectation value here, plus this overlap term. Okay, so what we really need to focus on is equation 5.24, which is listed right below, 5.24, and this is the overlap integral. And we'll see that that is referenced several times. So we already have the first chunk of this expectation done, but what we need to do is find this overlap integral, which will be used in both B and C. As you see in the actual equation 5.25, we have the expectation plus or minus, and then here is minus plus. So, with bosons, we already know that we're supposed to be on the upper signs, so we can really just focus on this overlap integral and quickly produce the results for bosons and fermions with this overlap integral and part A. So let's see what we need to do. The overlap integral tells us that we need to find the expectation value of where the two states overlap, i.e. in and L, in the same space. So we saw what the wave functions were for �ψn and �ψl, noting that 𝐶n conjugate is the same thing because it's all real. We're good there. Now it's just a matter of simplifying and finding a way to solve this integral, which we see that we have a square root of 2 over a, square root of 2 over a, both constants, so we could take them out. So we have 2 over a outside because we're squaring it. Good to go there. Remember that when we started this, a was the width of the well, so we run the integral from 0 to a, and we're good to go. Also note that n or L for these infinite square wells run from 1 to whatever other higher integer, and we're good to go. The problem comes in when we have these multiples of sine here with two different arguments. So we're going to have to use some trig to break that up into, instead of a multiplication, into an addition or subtraction. Let's see what we can do. Alright, fair enough. So whenever we use our trig identities, we can put that multiplication in terms of a difference here, and we just have to be careful when we do that we take into account the arguments of the cosines. Here, instead of just n or L, it's a combination. And that just comes from the sum difference identities. We've seen this a couple times throughout this book. We'll definitely see it again. We see here that we have n minus L and n plus L. So we definitely need to be careful there. I think color coding it makes it very easy to follow along with that and spot the differences. But now what we have to be aware of is that this 2 cancels with that 2. Alright, whatever. Easy algebra there. What we do have to be careful of is the fact that when we distribute this x and do this cosine and that cosine, you actually write that in, distribute that into here and here, we get two integrals of this form here. And with that, what we can see very quickly is that those two integrals, when we use an integral table as given in the book, actually on the back cover, we see that we get a form of 1 over a squared cosine ax plus x over a sine ax. Okay, but let's realize here that whenever we evaluate this with the limits of 0 to a, sine of ax will be evaluated at some multiple of pi. So with that, we know that sine at any multiple of pi goes to 0. So we're not going to worry about this term so much. That'll go away. What we do have to worry about is this nonsense here. And what we see after calculating it, which I would highly suggest you use Symbolab to help you with this because it is nasty, gross, or Mathematica. Whatever your tool of choice is, feel free to use it. I think it's important to see the physics of this, not deal in the integral calculus of it. That being said, whenever we do the form matching and get it all squared away, we see we get something pretty compact here, which is nice. But now we have to do some digging into the characteristics of what the cosine of n minus L and n plus L are. So let's go ahead and simplify that next. It's important that these coefficients that we're on from the 1 over a squared of the integral table get condensed and neatened up, and so we can factor out an a squared over pi squared, clearly canceling this factor of a with one of those, easy enough. Now back to the character of cosine. We know that n and L are both integers, right? So if we have any combination of n plus L or n minus L, that's going to be another integer. We have closure there. But we also know that cosine with any integer multiple of pi gets us to a value of minus 1 to the power of n plus L, meaning that it's going to be a multiple of negative 1, and the squared values give us positive 1 for when we're 0, 2 pi, 4 pi, so even multiples. And we know that we're negative 1 for the odd multiples. So that's pretty easy there. This is where I think one of the computers will help you in simplifying this expression, because it's not at all obvious as to how to tinker with this. But we can get the characteristic of the solution by knowing that cosine with integer multiples of integer multiples gives us a factor of negative 1 in some form or fashion. So, and then here we have the states here that we just condensed out after factoring from this curly bracket and that curly bracket, so we're good to go. But in order to simplify this, it becomes very important that we see here that, of course, with some cross multiplication and simplifying this denominator with after distributing them and all that other fancy stuff, we get a piecewise here. Namely, that this comes in whenever we simplify it when n and L are opposite parity, i.e. meaning that they're not in the same state, okay? And this makes sense because if they were in the same state here, right, n and L, if this is the same state, say 1 and 1, we would get a negative 1 to the 2 here, so that'd be a positive 1. Positive 1 minus 1 would lead to a 0 in this bracket, which would cancel everything out. If it's not, and they're not equal, then we could condense it like this. And for what the question gave us, the question told us explicitly that n was not equal to L, so we're good to go. And that's okay. We're in the right, we're good to go, so we are only going to focus on the top part of this piecewise definition, and we can simplify it down further. So let's see how we do that. All right. So with that, what we see here is, now remember that cross term that we had from the overlap integral was a, where's my pen? There we go. Was a magnitude, right? So we had a 2 times the magnitude of this expectation of AB. So we have to square this thing in the magnitude, so it gets rid of the negative sign. And we also have that we need to multiply by 2. So this 128 is 8 squared times 2. So we're checked there. The a gets squared, the n and L gets squared, the pi squared gets squared, so all that is looking good. Then here we have the joining of the distinguishable part with the overlap part. So that's pretty easy. And again, with bosons, we are told to look at the upper signs. So in the equation, these are the upper signs. And this leads us right to stop number 3, which is fermions, which we use the same result, but we use the lower signs. So lower here, and voila, we get exactly what we need. Again, both B and C only have the last term presented when n and L have opposite parity, which we know because they told us in the question n does not equal L. So we're good. Perfect. That brings us to the conclusion, and we saw that we were able to find the distinguishable particles. We were able to find the expectation for bosons and fermions pretty quickly from this, just calculating that overlap integral. That being said, this overlap integral is going to be hectic in a lot of other applications, and we have a lot of varying results when we actually have something that's non-zero. So because of this, we have to be really careful when dealing with these integrals and the separation distance, especially when the notation goes to R1 and R2, which could correspond to 3 separate spatial dimensions each. So be aware, notation might be deceiving, and we need to handle all these cases with care, especially when we're exploiting things of the nature with cosine, sines, and parity and all this other stuff. Just be aware of your bookkeeping and you should be good to go. That being said, we have concluded this problem, so let's get to the concluding remarks. Alright, so thank everyone for watching. That was a little quick fun. We saw in summary that we were able to cover a lot more ground with just calculating just a few things and using old results, which again save us a lot of time. That being said, a massive thank you to our patrons for this invaluable support, making all of this possible. Please consider subscribing and sharing to fuel this curiosity, or even becoming a patron yourself. New content is posted weekly to aid you in your curious pursuits, and especially with the articles, we'll again be doing more of those to help broaden the landscape of which you have a foundation on. And that being said, books, notes, and other reference materials are found below. If you have any questions, please feel free to reach out. As always, thank you for watching. Until next time, stay curious.